All right, and now we're going to talk about nerve innervation because the skeletal muscles are stimulated by a nerve impulse. And we call the end where a nerve goes to a muscle, we call that the neuromuscular junction. So that's where they connect. One nerve, this is interesting, one nerve can innervate or stimulate a variety amount of muscle cells. So then each time a nerve fires, all, this is important, all of the fibers that are innervated will contract. Does that make sense? All of them, because you cannot fire a nerve halfway. You can only fire a nerve fire or not fire. That's the end of the story. And so what we describe as a motor unit is a nerve with all the muscle fibers that it innervates, all the muscle fibers that it stimulates. So each muscle has many motor units, but then each nerve stimulates multiple fibers underneath it. So a motor unit is all the fibers one nerve innervates. So if we have a motor unit that consists of a few muscle fibers, we can create weak contraction with great fine motor control. So that could be, for example, our facial muscles. But when we have one nerve innervate a lot of fibers, muscle fibers, we have very strong contraction, like your quads in the front, to make you not fall down. So they're more crude in terms of function. You can smile with your quad and make that little small contraction, but of course you have much more force. So the more motor units recruited at the same time, the more muscle fibers innervated by one nerve, the stronger the muscle, and the more motor units recruited at the same time, the stronger that muscle's contraction will be. So we can gradate a muscle contraction by depending on how many motor units we fire. I know, now we're getting technical. Let's just go through this and let's see. Yeah, we're almost there. So muscle metabolism is also important because muscle, well, we need energy. That's ATP. And energy is mostly formed in the mitochondria. So muscle needs a large amount of this energy and needs, therefore, many, many mitochondria. However, the muscle's easiest fuel to get is convert ATP to glucose. Convert to ATP is glucose. So in normal times, what we could do, we take the glucose. We actually have a lot of glucose around because we get all these glycogen storages in there. We take the glucose, go to the mitochondria, make tons of ATP. Nice to do that. When we don't have enough oxygen though, because muscle contraction will squeeze the blood away and we might be not having enough oxygen. So we have a lack of oxygen. And when that's the case, we have to make ATP anaerobically. And I keep this here up because anaerobically means without air. So there's no oxygen. Oxygen, air, synonyms for this stuff. So then this makes us a few ATPs by just converting glucose to the first few steps where we don't need oxygen, because once we get into that mitochondria, we need oxygen. But the problem is we don't make much ATP, we use a lot of glucose, and we have a buildup of lactic acid, a lactate. That has to be going to the liver to be reconverted back to glucose, and that tires muscle easily. So the other thing we have is we have stored creatine phosphate, and that can be very useful to rapidly phosphorylate ADP back to ATP, which means we put a phosphate back on. But then we have to reconvert the creatine phosphate later. And that's what I have here as a table, essentially. So that's one that's just print out and study a couple times. But the basic function is energy is best created with having oxygen around, because then we can go to the mitochondria. If we have a lack of oxygen, we need to produce more ATP by anaerobically, which creates lactic acid buildup, or we need to use up our creatine phosphate storages. And of course, that will tire us as well, or fatigue us, I should say. When we describe muscle fibers, we also go and differentiate a little bit further. We have slow twitch fibers and we have fast twitch fiber. A twitch is the length of a contraction. So some muscles are slower to contract and they don't contract as forcefully, but they can hold a contraction longer. they use a lot of oxygen and they harbor a large amount of myoglobin, which is kind of like hemoglobin, but it has like a magnet that's very strong to oxygen. So when the blood travels by muscle fiber, it just sucks the oxygen out of it. So that's kind of cool. But that can give us then, of course, a lot of oxygen for those muscles, and those muscles are slow or tonic fiber muscles, and we use them mostly for posture. And then we have muscles that are faster. Some of them are very fast. They can be very forceful, but they tire easily. They look pale in comparison because they don't have as much blood going through it, because they rely more on this fast, quick spurt that is less aerobic, that has more anaerobic components to it, how we get the ATP. And that brings us to isometric versus isotonic muscle contractions. And when we look at a muscle contraction, we can have it be that the muscle length changes, like lift something off the floor, or we can have the muscle just holding a weight and don't lengthen or shorten. And so when we look at these terms, the isometric contraction is when you just hold something. Iso means same, and metric refers to meter. So that's just when you're holding a weight or something in your hands. And then on the other hand, you have an isotonic contraction, and tone is the tone of the muscle is the same, so to speak. And that's when the muscle actually moves. So when you're holding a 3-pound weight like this, you're just holding it and carrying it, that's an isometric contraction. And when you actually shorten it and lift the weight up, it's an isotonic contraction. And the isotonic contraction, we can further differentiate. I didn't write this down here, but one that a shortening is a concentric contraction, and a lengthening, when you let the weight down, is an eccentric contraction. So concentric shortening or eccentric lengthening. I know, it's kind of interesting, but it's getting a little tiring, isn't it? Oh, and this brings me to the origin and insertion. We did talk about that a bunch of times. So when we look at the muscle attachments, we have a muscle attachment on the bone that's in a place that sort of stays more stable, that doesn't really move. And then we have a muscle attachment on the bone crossing the joint on another bone, and that part of the bone moves. So the part of the bone, the one attachment that doesn't move is known as the origin, and the one attachment that does move is known as the insertion. We have muscles like, let's look at the biceps, and behind it we have the triceps. So we have a muscle in the front. The bicep contracts, then that muscle is known as the agonist. And then we got a muscle that does the opposite motion, and in this instance is the triceps in the back of the arm, and that's the antagonist. When an agonist contracts, the antagonist neurologically has to relax. Otherwise, you can't get a muscle that can't move a joint. And then we also have muscles that help balance the motion and make sure the motion works smooth and all that. And that's known as a synergist. See here, syn means together, not a syn, S-I-N, a syn, S-Y-N. Synergist means together. So that's a helper. So that's about it for that part. And, 2 more slides, huh? Muscle shapes, that's not that complex. Well, there's one thing that's really interesting here, actually. Muscle comes in multiple shapes. We usually have a tendon, anchor the muscle into the bone, and the head, but then it goes into a belly, and then it anchors into another bone. And what's interesting about the fiber arrangement is we have parallel arranged fibers, and they are long, but they sort of have little lifting power because the whole muscle needs to contract before the length changes. And it's not that powerful. So biceps is like one of those, for example. But then we have other ones that have fibers that insert into a tendon at an angle, and they are shorter. So they're like, this is one of them. See, you have this like long tendon, and you have fibers that are short anchoring into the tendon parallel. The muscle contraction is actually this way, but that the fibers anchoring into the tendon at an angle. And so that creates a great amount of lifting strength. So that's kind of an interesting one. So the pennate muscles, penna means feather. So it looks like a feather basically. We have a unipennate, we have a bipennate, and we have multipennate even. See up here. So that just depends how many sides the stuff comes together. One is unipennate. If it comes from both sides, it's bipennate. And then this one has something in the middle as well. That's a multipennate. Tendons, to just talk briefly about that, since we haven't probably talked about that yet, are bundles of collagen fibers with great tensile strength. And they are transferring the force from the muscle to the bone. And we have flat tendons some places, like in the thigh on the outside, we have this IT band thing. That's a flat tendon, and we call that an aponeurosis. I know, aponeurosis, weird term. And lastly, but leastly, we have auxiliary structures. These are mostly used to reduce friction when the muscle does its work. So that way we have a lot less friction in the force. We have minimum reduction in the force because friction will slow everything down. And plus it heats everything up, so we get inflammation, and that wouldn't work out. So we have different ones. We have muscle fascia. That allows the muscles to glide over one another. Although fascia is a topic that's getting more and more attention in the applied sciences, and so we're probably going to learn a lot more about fascia in the future. Then we have synovial tendon sheath, and those help glide of tendon over bony protrusions. So those are like structures that are similar to joint capsules that are fluid-filled things, and the fluid gives you the cushioning effect and the cooling effect. We have synovial bursa, and those are very similar again, but those are sort of like pillows, water pillows, that cushion areas that need protection. And then we have the sesamoid bones, and I explained those previously, like the patella, the kneecap, where if we were to bend the knee, if you stand there and you bend the knee in a 90-degree angle, and you have the quad just coming straight down right to the tip of the knee and go straight down in a 90-degree angle and anchor to the front of the shin bone. And if you want to bring that leg up, if you want to straighten that knee out, you would have to exert a lot of force until it overcomes the 90-degree angular force it needs to transmit to pull that knee up. And then you have no control of how fast that knee will come up once it starts pulling. But when you have a patella in here, well, this knee's not bent. If this knee's bent, you see there's a more rounding effect of this tendon that anchors into here. And so therefore you can then contract the muscle more uniformly, and the knee straightens out in a uniform speed according to the force exerted by the muscle. Well, anyway, that's a lot of stuff, isn't it? So let's leave it at that, and I'll see you in class.